So this m is the local Mach number, velocity by speed of sound. This m star. So this is local Mach number. So this is characteristics Mach number. Okay, so the m star is the characteristics Mach number. Here the definition is V by A star. Okay, so the m is local Mach number that normally we use instead of velocity. Everywhere in the supersonic we will use Mach number V by A, and this m star is the imaginary one. This is not the real. This is the real one. This is the imaginary one. So just for the reference condition, we are using this characteristics Mach number. The main application is, for example, the next unit and all, we will use the shock polar. Shock polar means it is a graphical representation of oblique shock wave property. That is how the oblique shock wave properties varies for different Mach number. For that, we will draw the graph. So these curves represent for different Mach number. This may be for 5, this for Mach number 50, this for Mach number 500. Up to Mach number infinity, there will be a graph. So from this graph, once you know M1, then you can find the Mach number changes across the oblique shock wave. So for that purpose, we are using this shock polar graph that we will study in second unit. So here they have taken Mach number up to infinity. So if you properly draw all the curves, then it will be difficult to fit all the infinity Mach number curves within the single sheet. So instead of this local Mach number, they are introducing this imaginary Mach number V by A star. So we are going to derive the relation. From the relation, if you take the Mach number, the values varies from 0 to infinity. But if you take this m star, imaginary characteristics Mach number, then the value is varying from 0 to 2.45. Okay. So instead of infinity, maximum we can get this value as 2.45. So now for this value, we can easily draw the graph. It will be clearly understandable. So for that purpose only, they are using this reference imaginary characteristics Mach number. Is that clear? And sometime a few used to confuse this m star with the sonic. But sonic is different. This m star is different. For example, if you take the CD nozzle, for example, here the flow is subsonic, M1 is less than 1. Assume properties P1, T1, rho 1, velocity is A1, speed of sound is, velocity is V1, speed of sound is A1, like that we have property. And on the throat, so we have Mach number is equal to 1, and properties we used to denote as P star, T star, rho star. So here if M is equal to 1, then V is equal to A, which is equal to A star. Okay. And in the exit, we have supersonic, where we have M2, P2, T2, rho 2, V2, A2. So this M1 means simply V1 by A. This M is equal to simply V by A, both are equal. And here it is V2 by A2. This is the normal conditions. All this Mach number is called as local Mach number. At this location, what is the exact Mach number? And that M star I told, which is V by A star. So in this all station, I can find the M star also. This is a reference condition. So this is station 1, for example, this is station star, this is station 2. So at all these three stations, I can find this reference. So here I taken only static. So already we discussed stagnation, P0, T0, then sonic, T star, P star, etc. and all. So these are also called reference conditions that can be used in this station 1. So once you know M1, P1, you can find P01. If you know M1, T1, you can find T01. Like that you can find the stagnation and this station itself. Similarly, you can find P star, T star also. Because if you know M1, T1, you can find T star. M1, P1, you can find P star. Like that you can find the sonic also. So when the unknowns are more, for example, this is the duct. So here I have only M1, P1, T1, rho 1. But here you have to find M2, P2, T2, rho 2, P02, T02, P2 star. These many properties you have to find it. So unknowns are more. In that case, you can call these reference conditions. First, you can find stagnation properties, then sonic properties first in the station 1. With the help of that, you can find all the unknowns. So all these stagnation, sonic, etc. can be used as the reference condition if the unknowns are more. Okay, so like that, it all in the station you can find stagnation and sonic. So now in the station 1 we can find this M1 star because I know V1, I know A star, you can find M1 star. So this is local Mach number, this is characteristics Mach number. Similarly in this station also I can find M star, which is V by A star. V, A star, everything is 1. So here you will get 1. So this is characteristics Mach number. This is local Mach number. Both are equal here. And here I know M2. I can find M2 star, which is V2 by A2 star. Here also I can find A2 star, P2 star, T2 star, etc. and all. So this is characteristics Mach number. This is local Mach number. So if M1 is less than 1, then M1 star also will be less than 1. If M1 is 1, M star also 1. If M2 is greater than 1, M2 also will be greater than 1, but the difference will be very high. For example, if M2 is 10, then M2 star will be around 2.3 something. Like that, there will be a variation. So this is the relation. So what I'm going to relate, M and M star, V by A, V by A star. So in this derivation, first I'm going to relate A and A star. Okay, if I relate this, I can easily find the M and M star relation. So I am taking static in station 1, sonic in station 2, so that I can get the A star here. And whenever if you want to find velocity or Mach number, you should go for the energy equation. This should be the first option. So I am taking the energy equation, H1 E1 squared by 2 is equal to H2 plus E2 square by 2. Now apply this to this control volume. So before that, so this is my final equation, M star and M relation. So it has only M and gamma. There is no H term, CP term, R, T term and all. So I have to convert that energy equation like this, gamma and M term. So I don't want this H, U and all. So first I'm converting this H. So instead of H, we can write CPT. And instead of CP, we can write gamma R divided by gamma minus 1. Then this gamma RT can be written as A square. So instead of H, I can write A square divided by gamma minus 1. Okay, that only I substituted here. Instead of H1, A1 square by gamma minus 1. Instead of H2, A2 square by gamma minus 1. This is the first equation. Then this I am going to apply to this control volume. So in the station 2, I have sonic. That means U2 is equal to A2 is equal to A star. So instead of this A2 and U2, I am substituting this A star. Then simply rearrange it. So simply rearrange. You will get this term. Again, I don't want this A, U, A star term and all. I need only M and M star. So just divide this equation by U, so that you will get A by U. This get cancelled. A star by U. And we know M is U by A. M star is U by A star. Substitute. Again, simple rearrangements. You will get this final term. So energy equation. I don't want this H, U and all. So H I converted into A square by gamma minus 1. So this is the final equation. Then apply this energy equation to this control volume. In the station 2, it is sonic. So these two are A star. Then simplify, divide by U, you will get M and M star. Then rearrange, this will be your final equation. So now we can check it. So here if you apply M is equal to 0, then M star also will be 0. And if you apply M is equal to 1, then This, if you simplify, you will get gamma plus 1. So gamma plus 1 divided by gamma plus 1, again 1. The m is equal to 1 means m star is equal to 1. And if you apply m is equal to less than 1, then m star also will be less than 1, but the difference will be very less. For example, if there is 0.9, it will be 0.91 or something. Only this much variation will be there, m and m star. And if m is equal to greater than 1, m star also will be greater than 1. For example, I told if it is 10, it will be 2.3 something. Then finally, for m is equal to infinity, so actually if you substitute infinity here and here, it will be an indeterminate format. So this cannot be solved. But here they are doing some other simplification. So instead of m, they are substituting infinity. If this is infinity, this term, then this 2 is negligible. So remaining term you have is gamma plus 1 into infinity divided by gamma minus 1 into infinity. Is that clear? If this term is infinity, then this 2 is negligible. So the final is gamma plus 1 infinity divided by gamma minus 1 infinity. Then they are cancelling this infinity and infinity. With that they are getting m star is root of gamma plus 1 divided by gamma minus 1. We know gamma value is 1.4. In that we are getting it is 2.45. So Mach number ranges from 0 to infinity. This m star ranges from 0 to 2.45. So it will be easy to draw the graphs and all. So I have around 10 problems. In that, half of the problems I prefer solving using the formulas. For remaining problem, we will go for the gas tables. Immediately, if you start with the gas table, you may not familiar with the formulas. So here the first problem. So across the normal shock wave, they mentioned the properties. So they are given T1, T2, P1, P2. Using this, you have to find dH, dE, and ds. Actually, two equations are there. This is in terms of temperature and pressure. The another one is what we derived, CV ln T2 by T1 plus R ln V2 by V1. So two equations are there. Actually, in my notes you can find both derivations, but I used only this for the isentropic relation. So this is dH, this is dE, this is ds. So we should know P1, P2 value, T1, T2 value, CP, CV value. So for air, you know the CP it is 1005 approximately, CV is 717. All other value it is given here, T1, T2, P1, P2. Simply substitute. So dH is 4.038 joule per kilogram Kelvin, and dE is 2.88 in 10 power 5 joule per kilogram Kelvin, and S2 minus S1. So CP R value we know, all this pressure temperature you know. From that you got 258 joule per kilogram Kelvin. And this is the next problem. So here they consider flow over the aerofoil. So I'm drawing the control volume. So they mention free stream properties P infinity, T infinity, and pressure on the aerofoil it is P1. What you have to find is rho 1. Here what is the procedure? So T infinity is known, P infinity is known, P1 is known. Using that you have to find rho 1. What is the procedure?
So P equals to rho RT. There is temperature also given at stagnation point. So
P is equal to rho RT.
So we can find T1, sir.
Okay, how to find T1?
So the formula for this thing, isentropic flow is there, so we can use
just a formula relation between what is that?
Sir, or
T2 by T1 equals to T2 by T1 power gamma by gamma minus 1 we can use.
Okay, that is if you apply here it will be P1 by P infinity is equal to T1 by T infinity power gamma divided by gamma minus 1. This is what you are telling, right?
So we can
Yes,
also
sir.
use gamma 2 by gamma 1 there instead of P1.
Sorry.
No, sir, no, sir.
This is one relation. Using that, you can find the T1.
Then, sir,
So,
rho 2 by rho 1 also has a relation with T2 by T1, sir.
Rho
We can
2
write
by.
rho 1 by rho infinity
Okay.
equals to T1 by T infinity power 1 by gamma minus 1.
Okay.
we can find the rho
And sir,
infinity as P
P2 is
infinity
equals
equals
to
to
rho R
rho
T2, sir.
infinity RT.
And P1 equals to rho R T1, sir.
So from this, what are we going to find from this equation?
So we can find the gamma, yeah, rho 1, sir.
Rho
And
infinity also unknown.
Sir, P equals to rho RT, we can find rho infinity, sir. Because we have P infinity and T
So you
infinity.
are telling this equation, huh? P infinity is equal to
Rho
rho
infinity R
infinity
T
or P
infinity.
infinity. Okay. Okay. So actually, every problem there are n number of possibilities to solve it. It's up to you. You can proceed with anything. The value will be same only. But I think this will be easy. So you can take first pressure and temperature relation. So P1, P infinity, T infinity is known. You can get the T1. Then you can use this relation. So P1 is known. T1 just now we found it. This is gas constant. From that you can find the rho 1. So only these two steps. Correct?
Yes, sir.
No need of these formulas. This also correct. I'm just telling this also one method. Hmm? Let me check how did I solve this. I think I proceeded with the way you explained. I found rho infinity, etc. and all. Do you have my notes? No, right?
No, sir.
Okay. I think compared to this, it will be very easy, right? These two steps.
yes, sir, because steps would
Yes, sir.
increase in additional P infinity 1, sir. I think so,
Yeah.
yes, sir.
Yeah. So here just two terms, two steps. It will be easily solved. Okay. Here you see how we have solved. So they have taken first density and pressure relation, and using the ideal gas law, we know P infinity, T infinity, R value also known. From that they found the rho infinity. Then they substituted here. So P1, P infinity is given. Rho infinity just now we found it. From that they are finding rho 1 in 0.5404 kg per meter cube. So later if you want, using these steps also you can verify this result. Is that clear, this problem?
Yes, sir.
Okay, thank you. The next problem, flow through supersonic wind tunnel. So this is the reservoir. This is the settling chamber. This is the CD nozzle. Then we have the test section. So here they have given reservoir conditions. P naught is given. Then at the exit, nozzle exit, pressure is given. So nozzle exit, pressure is given, and you have to find temperature and density. So T naught, P naught is known, P is known, and the condition is isentropic. What is the condition for isentropic?
The P naught is constant, sir.
P naught is constant, T naught is constant. So both are constant throughout the duct, okay, throughout the process. So now tell me how to find it, temperature and density at the exit.
So same formulas as before, sir.
Tell the formula, please.
Sir, wait, what
So
remember?
So
P1
Sir,
P
by
P,
naught by TE equals to T naught by TE power gamma by gamma minus 1. Power gamma by gamma minus 1.
Okay. Okay, with that you can find TE. Good. Then
So same if we just substitute like P naught by PE equals to rho naught by rho E power gamma.
that is correct actually. But we don't have rho naught. That you have to find it ahead. What you're telling is correct.
Yeah,
We
sir,
can,
there is that T naught and P naught is given, so we can use P equals to rho naught R T naught.
that's why this is correct. First you can find rho naught, then you can go for rho naught by rho E is equal to T naught by T power gamma divided by gamma minus 1. This is one way. Any other way?
So we have P naught by PE, so we can use rho naught and P naught relation easily.
Rho naught and P naught relation. So second method you are telling P naught by P is equal to rho naught by rho E power 1 divided by gamma, I think, formula. Okay, this is the second method. Any other method?
Sir, P is equal to rho R TE, sir.
Good. This is very simplest method. Okay, ideal gas law. P is equal to rho E R T E. P is given. T just now we found it. From there you can find the density. Is that clear? Three methods are there. In exam, whatever comes to your mind, you can proceed it. But this is the simplest method. Within a single step, you can find the answer. Got it? Good. Any doubt in this?
No, sir.
No, sir.
Okay. So here, yeah, we use that method, last method only. So first we used stagnation relation between pressure and temperature. So P naught P is given and the T naught is given. We found the TE. Then we went for the ideal gas law. P is known, T is known. We found the rho E. Okay. So from this we found the TE, which is 259 Kelvin. Then from this ideal gas law we found the density 1.359 kg per meter cube. Clear?
Yes, sir.
The next problem. So this is little bit difficult. So they mention on flow field. In the flow field, we know only the pressure 0.2 atm, and we have to find the compressibility for isothermal condition, and you have to find the compressibility for isentropic compression. So you know the compressibility equation. So minus 1 by specific volume, then dV by dP. So this is the general equation for both condition, isothermal and isentropic. What is the condition for isothermal? Isentropic, you told P naught is constant, T naught is constant. Isothermal,
Its static temperature is constant.
good. Static temperature is constant. So using these conditions, we are going to find dP by dV and substitute in this equation. Okay. So this is the solution. So first I will go with this isentropic. It will be easy for you. So you know isentropic relation. So this is the general one. Here I am going to find dV by dP. So I am taking one isentropic relation which relates this specific volume and pressure. So this is another form of it is P divided by rho power gamma is equal to C. Instead of rho, I have written V. Okay, so V is equal to 1 by rho. So this form we are getting in the isentropic relation. I need V so that I can differentiate this with respect to P. So I can rearrange first C divided by P, then take the power to other side. So V is equal to C by P, C by P power 1 by gamma, 1 by gamma. Now this is my V equation. This I am going to differentiate it with respect to P. So how I am splitting this means, this is constant, C into 1 power gamma is constant, and this 1 divided by P power 1 by gamma, I can write it as P power minus 1 by gamma. Is that correct? This term I am expanding like this, C power 1 by gamma, and this 1 by P power 1 by gamma I am writing P into P power minus 1 by gamma. Now we can differentiate with respect to P. This is constant, straight away I am taking this outside, and this is like x power n, then the answer will be n into x power n minus 1. Okay, so first n minus 1 by gamma, then this is n minus 1. Is that clear? How to get dv by dp? Should I repeat?
Yes, sir.
So you know isentropic relation, that is P2 by P1 is equal to rho 2 by rho 1 power 1 by gamma relation. The simplest form of that equation is P by rho power gamma is equal to constant. So we know specific volume is 1 by rho. So this equation I can write it as PV power gamma is equal to constant. So this you studied from the thermodynamics. So this is the equation I am going to take it to find this dV by dP. This is the first step. So I need V term. So if you rearrange, V is equal to C by P. Okay. So for example, V power gamma is equal to C by P, and gamma if you take this side it will be 1 by gamma, and further I am simplifying this. So V is equal to C power 1 by gamma and remaining 1 by P power 1 by gamma. This I am writing as C power 1 by gamma. This term I can write it as P power minus 1 by gamma. This 1 by, this is like this, right? This term 1 by P power 1 by gamma, that I can write it as 1 divided by P power 1 by gamma, and this time if you take to the numerator it will be P power minus 1 by gamma. That's what I written here. Is that clear?
Yes, sir.
Okay. So now we can differentiate this dV by dP. This is constant. Simply I am keeping this C power 1 by gamma, and this is like x power n term. So first n minus 1 by gamma, then x is P, then remaining, okay, formula is n into x power n minus 1. So n minus 1 means n is minus 1 divided by gamma, then minus 1. This is what I written here. Normal differentiation. Shall I clear it? Shall I clear this? These steps?
Yes, sir.
So we are getting this term. Then remaining and all simply a normal simplification. So they are taking this C inside. Okay. And this dou by dou P, they are substituting in the compressibility equation. So minus 1 by V into this dV by dP, they substituted. Then simplify. So another thing, instead of this C, they are substituting PV power gamma, because we don't want the C in the final term. Instead of C, they are substituting PV power gamma. So already we have 1 by gamma in the power, so get cancelled. So you are getting P power 1 by gamma into V instead of the C. The normal simplification is that you are getting tau S is equal to 1 divided by gamma P. So this get cancelled. V get cancelled. Remaining will be 1 divided by gamma P. So we know the gamma value, P is given. We found the value. Is that clear?
Yes, sir.
And another one tip. So always in the problem, they used to specify mostly P in terms of ATM. But whenever if you want to substitute in these steps, it should not substitute in ATM. It should be in Newton per meter square. Okay. You should not substitute in ATM. The conversion is 1.01 in 10 power 5 Newton per meter square. In this conversion only you have to substitute. So you should not substitute directly in ATM. Always you have to convert it into Newton per meter square. Then only you have to substitute. Otherwise you will get wrong value. In all the wherever you are getting this ATM, everywhere you have to convert that ATM into Newton per meter square. Don't forget. So this is the isentropic. Similarly, isothermal. So in the isothermal also, we have to find this dV by dP. So I know static temperature is constant. So I am taking this just ideal gas law. PV is equal to RT is equal to constant. This is constant. This is also constant. And I need only this V term. So if you rearrange, V is equal to RT by P. So this is the constant term. Now I can differentiate this term. V is equal to RT by P term I can differentiate. If you differentiate, so 1 by P, if you differentiate, it will be minus 1 by P square. So RT is constant. 1 by P is minus 1 by P square. Again, I don't want this RT and all because I don't have the T term. So I'm going to cancel the T term. So I can substitute this here. So V is equal to RT by P. So here if I substitute, I will get minus V by P. Okay. RT by P, it is V. So I will get minus V by P. So that only I am taking instead of dV by dP, minus V by P. Then V get cancelled, remaining only 1 by P. That P value in terms of Newton per meter square you have to substitute. Is that clear?
Yes, sir.
Okay, so this is the only problem, a little bit difficult. All other problems and all, it will be very interesting. Simply you have to take isentropic. And next problem, just a 4-mark problem. So they mentioned the velocity, they mentioned the temperature, you have to find H naught. Once you see the H naught, you know which formula you have to take it. What is the formula?
Enthalpy, sir.
Tell the formula. Stagnation enthalpy.
H1 plus V1 square by 2, sir.
2 is equal to
H2 plus V2 square by 2, sir.
okay, this is the general formula. So here they ask stagnation. That means at any one station, the flow is stagnant. Maybe here static, and here maybe stagnation. Okay, so now if you apply that, the equation will be H naught is equal to H plus U square by 2. Okay, so if they ask H, then you can take the general equation. They ask H naught. That means in any one station, the flow property is stagnant. So this is the final equation. Is that clear?
Yes, sir.
Okay. Then you know instead of H we can put CPT. Instead of H naught, it is CPT naught. From which one you have to find? Okay. So straight away you are going to find the H naught. So instead of H we can put CPT plus V square by 2. So Cp, you know that temperature is given, velocity is given, directly you can find the H naught, just a 4-mark problem. But only one difficulty, all the units are in British unit, it is not the SI unit, right? In SI unit, velocity we used to mention meter per second, and temperature we used to mention Kelvin in SI unit. This is the British unit. So here they mention velocity in terms of feet per second, and temperature they mention in terms of, what is it, R? It's a Rankine. At the last page, you can see the conversion table. So here you can, using this, you can convert meter to feet, meter per second to, what is the velocity? Meter per second to feet per second. So all the conversion you can do it here. For the class purpose I'm telling, but in the exam there is no British unit. We will ask only the SI unit, meter per second, Kelvin, that only we will ask it. So if you know the Rankine, you can convert it using as a Kelvin. And so here they used SI unit and British unit. Instead of meter, they are using feet. Instead of kg, they are using LBM or slug. Mostly they will use slug. And instead of Kelvin, they are using Rankine. And instead of Newton, so they are using LBF, pound force. LB means pound force. Like that, they are using different terms. So instead of energy, joule, instead of Newton meter, they are using, instead of Newton, it is LBF, instead of meter, it is feet, LB feet. Otherwise, instead of joule, they will use BTU, British thermal unit. Like that, the units will vary. In this problem, so the first step, if you want, you can convert this feet per second to meter per second and Rankine to Kelvin. Then you can proceed with the problem. Or here, I just kept it as a feet per second and the Rankine itself and proceeded. So this is the equation we discussed. H0 is equal to H plus T squared by 2. And instead of H, I am taking CPT. So T they given in Rankine. V they given in feet per second. And if you use the British unit, all the CP value, specific gas constant, everything will vary.